Hello, welcome to the fifth and final short lecture on voltammetry, where I'll just introduce you to a few more techniques that we can use as analytical electrochemists. And the reading list still hasn't changed at all. Polarography is a voltammetric technique used for analytes where the surface condition of the electrode can rapidly foul or deteriorate, for example through roughening. For example, the buildup of contaminants of platinum or gold can rapidly reduce the reproducibility of their measurements. The drop-in mercury electrode employed in polarography overcomes this by using a fresh drop of mercury every few seconds, exposing a clean surface every time. One of the issues with this, and indeed with any type of voltammetry, is the buildup of charging current. The redox processes we investigate by transferring electrons at the metal surface, known as Faradaic processes, give us current responses largely proportional to the amount of reagents transformed by electron transfer. The buildup of ions at the surface due to attraction or repulsion to the polarized electrode, which cannot undergo an electron transfer, are called Faradaic processes. The buildup of charge and of absorption of non-participating species at the electrode surface interfere with our measurement of the Faradaic current. With the mercury electrode, both the re-establishment of the surface and increasing the potential lead to significant charging current. The graph on the left illustrates how the current responds to a sudden increase in potential. The Faradaic current initially surges to the same level as the charging current, but then settles to a steady value. The charging current, whilst initially large, dies away to zero as the charge dissipates. To ensure a steady current and to ensure none of the contribution to that current is non-Faradaic, the potential is ramped in sharp steps and the current is sampled only towards the end of the voltage step, just before a new drop is formed. The polarogram on the right shows how the sampled current against voltage gives a smooth curve up to the diffusion current. Another very useful analytical voltammetry technique is stripping voltammetry. In stripping analysis, a dilute solution is concentrated into a mercury electrode by reduction to form the mercury amalgam. So the potential is swept and held at a negative potential to reduce the oxidized cadmium, lead and copper ions in the diagram into solid mercury amalgam. And there they are, all absorbed into the mercury. This process is then reversed. The voltage of the electrode is swept from negative to positive to oxidize the amalgamated species and then release them back into solution. This is a highly sensitive technique as the analyte is concentrated from a dilute solution. The voltammogram on the right of your screen shows the current versus potential and the oxidative sweep of a honey solution. The dilute solution has been reduced into a mercury film at minus 1.4 volts. The grey line is the voltammogram for the same solution but without the prior reduction. This illustrates the benefits of concentrating the ions compared to relying on only the surface processes to generate the current, and its obvious implications for sensitivity. When compared to known standards, the concentrations were found to be adequately quantified even though they were only present in parts per billion. The same technique can be employed for oxidized species that have been allowed to adsorb into the mercury. So the voltammogram below shows the trace for iron 3, which has been complexed from seawater with dihydroxynaphthalene. The complex has been allowed to adsorb into the mercury, and the voltammogram shows the current response as it is reduced to iron 2. The concentration of iron 3 in the seawater has been ascertained through standard addition. So standard addition involves standards of known concentration being added to the sample so that we know how much precisely the amount of iron 3 added is. The difference in relative heights of the peak currents should be proportional to the difference in the concentration. So here the difference in concentration between 100 parts per million iron 3 solution and 50 parts per million iron 3 solution should be 50 parts per million. Correlation to this peak current height and concentration can be used to find the concentration of the unknown. You would have encountered cyclic voltammetry before in the course with Andrew. Cyclic voltammetry is a very widely used technique as it yields an array of qualitative and quantitative data in a single experiment. The voltammogram is obtained by sweeping the potential in the cell from low to high potential and then reversing the sweep from high to low. Here I'm showing you a characteristic trace for a reversible reaction. O2 is reduced to the O2 minus ion with an onset of reduction at around minus 1.75 volts. As the voltage is made more negative, the current responds by increasing up to a peak around minus 2 volts. This peak corresponds to the point where the rate of reduction can no longer be maintained, as the O2 species can no longer be supplied to the electrode at a sufficient rate. The process is now transport, or in this case diffusion, limited. The reduction will continue at some level, but more slowly as the voltage increases and the current falls. At minus 2.25 volts, the reverse sweep begins, and we see an equal and opposite peak current develop. The current has opposite sign because the O2 minus species is now transferring electrons in the other direction, i.e. to the electrode, as it is reduced. This is an example of one electron reversible reaction, were the peak in either sweep not the mirror of the other, that would signal an irreversible reaction. Cyclic voltammograms can also demonstrate a sequence of reductions and oxidations, providing the sweep rate is low enough and the onset potentials are sufficiently well spaced. A lovely example of this is given for C60 or Buckminster fullerene, where each of the ionizations can be seen discretely all the way up to C66-. The Karl-Fischer titration is a widely employed method for quantifying trace amounts of water in samples of oil, food, solvents, polymers, and a range of other possible materials. On a larger scale, greater than 1 milligram water content, the titration can be performed volumetrically. For smaller amounts of water, the coulometric method, for which the apparatus is shown here, is preferred. In the main compartment, a stirred anode solution, coloured blue in the diagram, is dosed with a known volume of sample containing an unknown quantity of water via the septum. In the right-hand tube is a cathode solution separated from the main compartment by an ion permeable membrane. The cathode for this cell is immersed in the cathode solution, and the anode is on the other side of the membrane in the anode solution. The anode solution contains an alcohol, ROH, a base, B, sulfur dioxide, SO2, and iodide, I-. The anode of this larger cell generates I2 by oxidation of I-. I2 and water then react together with the alcohol base and SO2. Overall, SO2 is oxidized by I2 with the formation of ROSO3-. At the end point, when all the water is consumed, I2 will stop being consumed. The end point is detected by a bipotentiometric measurement. On the right of the apparatus, 2 detector electrodes maintain a constant current. The potential required to maintain that current is measured. Before the equivalence point is reached, the solution is rich in I- but low in I2, as the I2 is consumed in the titration reaction with water. To maintain the current before the equivalence point, the voltage needs to be high. Once equivalence is reached, excess I2 is present. I2 is reduced at the cathode, producing I-, which carries the charge between the electrodes and greatly reduces the potential required to maintain the current. This drop in voltage signals the endpoint of the titration. Okay, so that was the final slide, and this is the end of the lecture series. Look forward to seeing you all in the lessons.